Hello, this is Math 2115 coming to you from the College YouTube page, and the title of this lecture is Introduction to Proofs. I encourage you to be an active learner as you're watching this video. A mathematical proof is an inferential argument for a mathematical statement, showing that the stated assumptions logically guarantee the conclusion. The argument may use other previously established statements, such as theorems, but every proof can, in principle, be constructed using only certain basic or original assumptions known as axioms, along with accepted rules of inference. This is a very early Egyptian mathematical document that's called the Rhind Papyrus, and yeah, I just threw it up here for math history's sake. Now, this idea or topic of mathematical proof may be new to some of you. It does touch on some very serious math and computer science tradecraft, so please give it your kind attention. We'll deal with mathematical systems, and mathematical systems consist of axioms, definitions, and undefined terms. Axioms are assumed to be true. Definitions are used to create new concepts in terms of existing ones, and there are many definitions in this course. Some terms are not explicitly defined, but rather implicitly defined by axioms. Within a mathematical system, we can derive things that are called theorems. A theorem is a proposition that has been proven to be true. Sometimes we will ask you to prove theorems or prove things. Special kinds of theorems are referred to as lemmas and corollaries. A lemma is known as a helping theorem, so it's usually not too interesting in its own right, but it's useful in proving another theorem. A corollary is a theorem that follows easily from another theorem, and sometimes corollaries are quite useful. An argument that establishes the truth of a theorem is called a proof, and logic is a tool for doing that proof. That's why we covered logic before this chapter. Professional mathematicians often work to prove theorems. Computer science folks are interested in proofs that their code works, and sometimes computers are used to prove theorems. Computers are often used for empirical inductive insights, trying to think about what theorems might be true, and you can look at a bunch of examples that way. There is a difference between inductive and deductive reasoning. Inductive reasoning is just looking at a bunch of examples. Deductive reasoning is really using logic. Both have their place, but proofs require deductive reasoning, and that is where logic is a prime key. We'll talk about systems, and some of the systems you know about. You know of Euclidean geometry probably. You might not know of non-Euclidean geometry, but we'll focus mostly on Euclidean geometry in any examples we do. We've learned about set theory in this course, and you've studied the real number system for most of your life, and we'll do some proofs with that too. So those are systems that you know. There are other systems that you will learn in this course about graph theory or graphs, Boolean logic circuits, and computer algorithms. Moreover, there are many proof techniques that you will learn, and that's something we're focusing on in this chapter. In this lecture, we will focus on direct proofs and counterexamples as a means of proving a statement is false. A direct proof assumes that a bunch of propositions are true, and then, using those assumptions, as well as axioms, definitions, and previously proved theorems and rules of inference, showing directly that a conclusion is true. So it says, if this is true, then this is true. In a theorem, there is an if part, called the hypothesis, and there is a then part, called the conclusion. It's often useful to identify those and keep track of where you're trying to go. Here's a definition from your book. An integer n is even if there exists another integer k such that n is equal to 2k. That really means it's divisible evenly by 2. An integer n is odd if there exists an integer k such that n is equal to 2k plus 1. That means you have a remainder of 1 when you divide by 2. It's not a multiple of 2. So here is an example of a direct proof. This could be something I could ask you to do on a test or quiz or something. I could say, prove the sum of any two odd integers is even. Now, I want to note right now that 3 plus 5 equals 8 is not a proof. I am taking two odd integers and adding them together and get 8, but this is just one example. That might lead you to believe, oh, maybe that is true, but this is not the proof. And I'm going ahead. That would probably be the only thing I would give you is this part stopping with even. But let's, since we're beginning this, talk about, so what's the if part and what's the then part? Well, the if part is we're going to take n1 and n2 are going to be odd integers. And our conclusion that we have to show is that the sum n1 plus n2 is even. You know what to do. Let's see how you did. So here is my proof. So we'll start assuming the hypothesis is true. So I'm going to say I'm going to take n1 to be 2k1 plus 1 and n2 to be 2k2 plus 1. These k's have to be different, or at least they could be different, and n1 and n2 are probably different. And the reason that we can do this is that this is the definition of odd integers that we just had, and both k1 and k2 are integers. That's your hypothesis. And then what we're going to do is, let's look at n1 plus n2. Well, if we add n1 plus n2, based on this definition, so we're adding 2k1 plus 1 plus 2k2 plus 1. And if we add that and do some algebra, that is 2 times k1 plus k2 plus 1 and 1 is going to be 2. And I can factor the 2 out of both those, and this can be 2 times k1 plus k2 plus 1. Those are just properties of real numbers. But look, now I have n1 plus n2 is equal to this business. And this business is 2 times an integer, because these are going to be integers. So this is 2 times k, where k is defined this way. So the reasons for this is the sum of integers is an integer. That's called the closure of this set of integers. And it's also substituting capital K just because it's easier to write than all of this stuff. So look what we have. We have the first is equal to the second, and the second is equal to the third. So the first is equal to the third, where k is an integer. That's called the transitive property. That's the first equals the second equals the third, therefore the first equals the third. So we have proven that n1 plus n2 is even because of the definition of even. It's 2 times an integer. So we have now proven our first theorem, and that's an example of a direct proof. Here's another direct proof, but we're using a different system. This is geometry, and we're going to prove here the Pythagorean theorem. Now this is a summary of what the Pythagorean theorem says. You have a right triangle, so that is one of your assumptions. And what this says is, and right triangle means there's a 90-degree angle there. And the Pythagorean theorem states that the length of this side, one of the legs, squared, plus the length of the other leg squared, is equal to the hypotenuse squared, the length of the hypotenuse squared. And that's true in any right triangle. And written as something you probably remember, you say, oh, a squared plus b squared equals c squared. Okay, you know what to do. Let's see how you did. Well, you've got your picture, and we need to, okay, so the hypothesis is, gee, I have a right triangle that looks like this. There's my 90-degree angle. I have legs AB, and that side is C. Now, this is a bit of a geometry proof, because what we're going to do is take a right triangle that looks like that, A, B, and C, and in fact, we're going to take 4 of them. 1, 2, 3, 4. We're going to glue them together in this way. And look, that makes a square because I got A plus B, A plus B, A plus B, and A plus B. And there's another square inside that is C, 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 and C. Now I'm kind of glossing over proving that these are 90-degree angles in here, but it can be shown pretty easily that they are. And this really isn't a geometry course, so I'm not going to dive into that too deeply. Okay, so the area of the big square, that's the one that has A plus B as the side, is going to be each side times itself, just A plus B times A plus B. But that area of the big one has to be the area of the pieces. So first, if we look at the smaller square, which is the yellow square in this picture, that's just c times c, or c squared. And then each of these triangles is the area of a triangle is 1/2 the base times the height, so that is going to be a times b over 2. And I have 4 of them, so I add them all together, and so what I get for this is that the area of the big square is c squared plus, and if I do this arithmetic here, I get 2ab. But both areas must be equal. So remember, this was the area of the big square. This was the area of the parts that made up the big square. So I set those two things equal, and I multiply this using rules of algebra, and I get a squared plus 2ab plus b squared is equal to c squared plus 2ab. And you got 2ab on each side, so you can subtract that from both sides. I get a squared plus b squared equals c squared. We have finished because we started with the right triangle. We used a bunch of reasoning, including rules of algebra, and we showed that the conclusion is true. A squared plus b squared equals c squared. We're done. This proof came from China over 2,000 years ago, and there are many proofs of the Pythagorean theorem, but this one works very nicely. And in fact, one of our presidents, James Garfield, had an original proof of the Pythagorean theorem. Here's another problem for us to prove with set theory, and this is problem number 30 from your textbook. Prove that if the power set of x is a subset of the power set of y, this is a good review problem for what that means, then x is a subset of y for all sets x and y. And you have to remember what subsets are and so on and so forth. You know what to do. Let's see how you did. I'm going to break this into cases, but the hypothesis is the power set of x is contained within the power set of y. That means if I take something in the power set of x, it also has to be in the power set of y, and we have to know what the definition of the power set is as well. So the hypothesis is that this is true, and the conclusion, what we have to show is that x is a subset of y for all sets x and y. Now I'm going to break this into cases because if x is the null set, that means that the conclusion, the null set is a subset of every set, and so that's vacuously true, but I took care of that as a detail. But now we're going to say, suppose there is something that is in set x. It's not the null set. So we pick A, an element of x. Then the set containing L is an element of the power set of x. You see, this is one of the subsets of x. It's the set containing something that is in x, which is what the power set of x is. But by assumption, by the hypothesis, which we're assuming to be true, the power set of x is a subset of the power set of y. So if I take something in the power set of x, it is also in the power set of y, and this is by the hypothesis up here. But that means that this singleton set is a subset of y because it belongs to the power set of y. But the only way that can happen is for A to be an element of set y. So you see, we started with x an element of, started with A an element of x, and we showed that A has to be an element of y. You see, that's what it means to be x to be a subset of y. You may want to review some of these definitions from the earlier chapter, and again in this course we build upon everything we do. Another thing we're going to talk about today is disproving a universally quantified statement. Recall that to disprove for every x p of x, we simply need to find one member x in the domain of discourse that makes p of x false. Such a value is called a counterexample. So you see, this is easy to do, but sometimes you have to be quite creative to do it. Here's a problem for your book. Here's the direction. They say, oh, look at the statement, figure out is it true, and if it's true, you should prove it. Otherwise, you can give a counterexample if you think it's false. And you got sets x, y, and z are parts of a universal set. Okay, so number 33 is the one I chose. For all sets x and y, either x is a subset of y or y is a subset of x. Now you have to figure out, is this true? And if it's true, prove it. Or is it false? And give a counterexample. You know what to do. Let's see how you did. This is false. And here's my counterexample. I can take the universal set to be 1, 2, 3, 4, those numbers. I can take x to be 1 and 2, and I can take y to be 3 and 4. So x is not a subset of y, and y is not a subset of x. So you see that's a counterexample. I showed that both of these are false. These are disjoint, and in fact, in this case, x and y form a partition of the universal set U. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.